Everyone. My name is Adam Noel, and I am an associate professor and also the director of student recruitment in the School of Engineering at the University of Warwick. And for this webinar session today, I want to go over introducing our department and also take a bit of time to talk briefly about the kind of research that I do at the university. So just a very bit briefly about myself. So I'm an associate professor in the Systems and Information Engineering stream. I'll talk a bit later in the talk about the different streams that we have in our school. I do also serve as the director of student recruitment, so that's why I'm doing this particular webinar with you here today. My original background is actually in electrical and computer engineering, where I did all my degrees in Canada. And my general research is that I'm interested in applying communications engineering ideas to cell biology. Now, I do have a bit more detail about this in a few slides, but if you are interested in seeing more information beyond what I covered today, you might be interested in checking out the YouTube channel that my research group has, where I have a number of videos up describing the kinds of research problems that we work on and kind of giving more of a background on this idea of communication engineering applied to biology. But for this talk today, it will mostly be about the School of Engineering. So I'll be introducing our university and our department, and then I'll use that to segue into an overview of my own research group and the kinds of problems that we work on. And then I'll spend most of the rest of the session to talk about what the programs of engineering look like at Warwick and really get into the teaching and learning experience and what are the features in our degrees that we have that we think help make Warwick stand out as an engineering school. I'll then go a bit more over how we support students through the student experience, the placements and career guidance that we provide to the students that are coming through our program, as well as a bit about the financial support and then the support that we also offer to anyone who has an offer to study in our department, whether or not they've given a firm acceptance. So first to introduce Warwick and the School of Engineering. And I'll transition first to talking a bit about numbers, even though we don't like to dwell on this stuff for too long, but since our numbers are great, we might as well talk about those a bit. So Warwick really does have an excellent ranking and reputation, both the university overall and the School of Engineering in particular. At the university level, in the most recent Teaching Excellence Framework, our university received a gold in all aspects. And this is quite significant. This was an achievement only met by 4 universities that are in the Russell Group, and the Russell Group are the research-intensive universities within the UK. Only 3 other universities had this ranking of gold overall. And that meant that we had gold for student experience as well as gold for student outcomes, and that the measure of student outcomes had to do with the anticipated performance of individual students based on how they came in versus how they completed in the end. So that was both of those ratings were gold, so we were able to get gold overall. We've had great ratings in some of the league tables, including the most recent Garden University Guide. We were 9th in the UK, 69th in the world in the most recent QS World Rankings. Some of the more specific metrics where we've done really well include being first in the Russell Group for work-based learning, the 5th most targeted university by the top 100 UK graduate employers, and also being in the top 10 in the UK for the highest earnings 5 years after graduation. And all those metrics relate to the university overall, particularly within our department. So our department is the School of Engineering. In the most recent Complete University Guide, we were ranked 6th in the UK. And first in the UK for our graduate prospect score. So that was a score of 100%. Furthermore, the university participates in what's known as the Research Excellence Framework, or REF. And so every 7 years, they do an assessment of the research across the UK. And in the most recent assessment, based on research done up until 2021, we had a rating where 93% of our research was rated as world leading or internationally excellent, which really reflects the high quality of research that's being done across the school. So more qualitatively, let's say, it's good to talk about why engineering at Warwick. And I think our real strengths are in the choice and the flexibility of our degrees. This includes a lot of industry engagement in both the design and the delivery of our programs. And we also try to give students opportunities for experience in the workplace. But in any case, we do support all the students with our signature pedagogies. This includes a personal tutor system. So every student is partnered with an individual academic as their personal tutor. This will be an assistant, associate, or full professor who they will be guided by throughout their entire undergraduate degree. Um, this is most important in the first year. You'll actually meet with your tutor every week, particularly working on mathematics tutorials. But you also meet with the tutor a couple of times per semester throughout the whole degree to go over individual progress, if you have any concerns, if there's any areas where you might need some help. And the tutor is a great signposting contact to make you aware of services and resources that are available all throughout the university for supporting your learning. We do create an inclusive curriculum and study environment. Our most recent ranking from Athena Swan is having a silver award. This reflects our commitment and our efforts to make sure that we have a diverse student body, accommodating a study environment, and an inclusive curriculum. Furthermore, we do have a lot of projects integrated into our programs. This includes a lot of collaboration with group members on group projects, and these help to build not only technical skills, but also social and commercial skills, which are really important for employability, as well as contributing to the overall student experience, basically making it a lot of fun to study here. And last but not least, we really do integrate interdisciplinary teaching and learning. And this is facilitated by having a general engineering school. So all of the different disciplines of engineering are all housed under one department. So we do work closely together across the different disciplines. And I'll show some examples of this as I go further through this presentation. So the structure of our school, as I've already said, that we have a general engineering department. And this really does contribute to our ability to offer interdisciplinary projects, to have collaborative teaching and research, and have that all kind of integrated under one roof. We have 4 discipline streams within our department with over 100 teaching and academic staff. We're also supported by over 40 postdoctoral researchers. These are people with PhDs who are still contributing to research projects. And we have over 180 postgraduate research students. So these are students doing a research-based master's or PhD degree. Now, I mentioned 4 streams, but you'll notice here that there are 5 different columns. And that's because we have 4 of these streams are hosted within the School of Engineering directly. And then the 5th stream, which is manufacturing and automotive, this is hosted by our sister engineering department, WMG. They're a bit more industry directed, and so they operate a bit differently than our traditional engineering school. But they do have a lot of close industry integration, and we do work together on delivering programs. So there are a number of research areas and teaching resources that are provided by both of the departments for delivering on our degree programs. But overall, the 5 streams are civil and environmental. We have electrical and electronic, the manufacturing and automotive stream, which is hosted at WMG. We have mechanical materials and process, and we have the systems and information stream. And each of these streams include multiple research groups, and members of staff can be members of multiple research groups as well. So just as an example, I'm involved in biomedical and biological systems in my research, and I'm also a member of connected systems in the electrical and electronic stream. And so there's a lot of crosstalk and cross-pollination across our discipline structure within the department. Looking outward facing now, we do have many industry partners. These are companies that help to support industry visits. A lot of them co-supervise on projects, especially at the 3rd and 4th year levels. And quite a few also offer internships to our students. Just to recall some of the numbers I gave earlier, that we had a 100% graduate prospect score in the most recent Complete University Guide. And we've been the 6th most targeted university by the top 100 UK graduate employers. Some of these employers, I have a number of logos here. A number of these you might expect or not be surprised by, at least just by the West Midlands being such a manufacturing powerhouse. So you see a lot of automotive companies here like Jaguar, Land Rover, Tata Steel, Rolls-Royce, but also companies that you might less expect to be involved in engineering. So like large financial firms like HSBC and Deutsche Bank, and then more traditional manufacturing firms like BAE Systems and Dyson. So we really do have quite a broad number of partnerships with various members of industry. And this really helps to have build connections for our students, develop the professional network, so it helps them have connections with companies before they graduate, and it really contributes to the overall education experience. Now I'll transition from that now to talking a bit more specifically about my own research. And my research group is the Biophysical Communication Engineering Lab. And so the research vision that I have is I'm interested in combining cell biology with communications engineering. I have some examples of living cell systems over here on the right side. So whether we're talking about bacteria colonies growing on petri dishes, whether we're talking about neurons in our brain and in our nervous systems, whether we're talking about plant tissue, or whether we're talking about tumors, or really any other kind of environment where cells are growing. Many diseases that we can describe in these different systems are in practice the result in some kind of disruption to healthy cell signaling. And by cell signaling, I mean the mechanisms in which cells are trying to send signals to other cells. And so this is not just signaling, but also communication. So it is the case that cells talk to each other in a sense. And my research basically asked the question, what if we had the possibility of talking back? Is it possible for us to treat cellular diseases as communication problems? So with that in mind, my own research in my lab here is for studying how molecule signals propagate between cells, understanding how living cells form networks that transmit and receive information. And ultimately, I'm interested in designing strategies that will either support healthy communication or disrupt unhealthy communication. So my research group, we're the Biophysical Communication Engineering Lab. We're interested in applying communication theory to biology. And we basically have three main ways in which we do this. The first one is mathematical modeling. And this is really based on communication engineering and communication theory. So we try to describe and understand how signals propagate over time and space. And what makes this work unique compared to conventional communication engineering is that we're thinking about the propagation of molecules, so chemicals and how they spread around in a fluid environment between cells, and not electromagnetic wave propagation, which is what's usually used in conventional communications. With our mathematical modeling, we also try to measure performance. So, for example, communication success, can we describe, how many bits per second of information is able to transmit over our system in some period of time. We also work on simulation algorithms for exploring different environments. And for this, we mostly use particle-based simulations. So we try to predict how individual molecules might move and react. And a lot of times we'll repeat these simulations many, many times to come up with statistics for how a system behaves. Finally, this is lesser so, but quite important and certainly done with the support of our collaborators, is biological experiments. So we do look at practical experimental environments where we are adding molecule signals to environments that have cells living in them. And then we look at different ways of trying to track those signals to see if they can match up with the mathematical models we develop and the simulations that we run. So just to give you an idea of some of the applications that my group is working on right now, I can summarize this as blood, brains, and biofilms. And by blood, we're not looking at blood directly, but we're interested in microfluidic organ-on-chip systems. So these are lab-based testbed chips that are used to try to mimic the behavior of organs. And these chips have different compartments, and then each compartment will have cells from a particular organ. We had a project where we were working for a couple of years with AstraZeneca. And with AstraZeneca, they were interested in modeling the human metabolism, so basically how glucose is regulated. And so they had these organ-on-chip systems with different cells representing different organs that are involved in glucose regulation. So, for example, the liver and the pancreas. And so some of the modeling we've been doing is try to understand how molecules move around in that kind of environment, and the clusters of cells that mimic the individual organs. We're trying to model how molecule signals are able to kind of penetrate inside these organs and describe how long it takes for molecule signals to get in, what might happen to the molecules while they're inside, how long it might take molecules to get out, and so on. For brains, we've been looking at some of the signals that are used in neurons for kind of supporting healthy neuron operation. So when we talk about neuron communication, a lot of people might be familiar with action potentials, which are kind of these high-speed signals that are sent along neurons, and they allow, for example, if you stub your toe, a message travels very, very fast up to your brain, up to like a couple hundred meters per second. But for some of the support signals, they actually get carried much more slowly. And there are mechanisms inside of neurons that kind of take molecules, put them in a container, and actually carry them along different tracks that are inside the neuron cells. And so some of the work we've been doing is kind of modeling what happens to these molecules as they're being carried. And we're interested in how disruption in that carrying of molecules can end up being a factor contributing to neurodegenerative diseases like Alzheimer's. The last big topic we're working on right now is in biofilms. So we're interested in growing bacteria on these plates. So these are plastic plates you can grow in the lab, and you can have bacteria kind of growing on top of these different colonies. And we're working with bacteria that have been genetically modified to light up if there is a certain signal present. And so we're doing some mathematical modeling and experiments and also simulations to try to predict which bacteria will light up where and when they'll do that. And yeah, the work in that is all ongoing. So we have these three different projects. I do have three QR codes here. These will each one will take you to a recent paper from my group that's been looking at each of these problems. So if you're really interested in hearing more about my research, you can check out those links and read some of the research that we've been publishing on these topics. But now I'll take this back to talking more generally about the school. So now I want to talk about kind of the details of the engineering degrees that we have here in the School of Engineering. So I've talked already a lot about interdisciplinarity. I hope that's been evident, for example, in my research, how it ties together really different distinct branches, not only of engineering, but also of science. But we find that kind of in any kind of modern project of something being built and created, we can often find elements that involve the different streams of engineering. So I give it as an example here, the construction of a new building and how the different, the four streams, at least within our department, can be involved. I think it's natural for people to picture civil engineering is involved in construction of a new building. Obviously, this can include elements like choosing resilient materials, having systems in place to monitor the structural health of the building, not only as it's being constructed, but also while the building is in use. We also find that there's contributions from mechanical engineers. This can include the design and installation of control and HVAC systems, so how all the heating, ventilation, and air conditioning work, having combined heat and power units to be able to make the building more comfortable. On the electrical side, of course, we have all the power systems, and we have the sensors and security. We have all the electronics that are driving perhaps the mechanical systems as well. And then finally, for systems engineering is probably the hardest to really define, but it really is kind of at the interface between different types of systems. And by different types of systems, I'm talking about, for example, the heating with the power or the power with the layout of the building, while also considering holistic factors like how people actually interact with the building. So making sure that a building is accessible and is comfortable, and that all of the subsystems within the building are interfaced correctly and that they're working as required. And we can find all kinds of say, modern manufacturing or engineering projects, and they all involve interdisciplinarity, whether we're talking about healthcare and the design of biomedical systems and technology, whether we're talking about space communications, whether we're talking about modern cars, whether they be electric or fuel-based or hybrid of the two. Obviously, all the large transport infrastructure that we have, including bridges, trains, and so on. And even in our smart homes. So the fact that you have now that your phone can talk to your heater and can talk to your smart fridge, we're really seeing a plethora of technologies being developed that really have this heavy integration between different disciplines, and they kind of all help to make things work. So we really design our engineering degrees kind of around that focus and making sure that people are not only becoming specialized within a given stream, but also being able to have at least a working knowledge of the basics of other streams. And that really helps to facilitate people working together on these big projects. So the degrees that we offer, most of our courses can be taken as either a Bachelor of Engineering or BEng, so it's a 3-year degree, or a Master of Engineering, that's an MEng, and that's a 4-year degree. So most of them are both. So under BEng and MEng, we have all the courses listed here in this column on the left. So we have Automotive, Biomedical Systems, Civil, Computer Systems, Electrical and Electronic, General Engineering, Manufacturing and Mechanical, and Systems. So those are all available as BEng or MEng degrees. We also offer a business management degree in partnership both with WMG and also the Warwick Business School. That's only available as a BEng, so that can only be done as a 3-year degree. To any of these degrees on this page, it's also possible to add an additional year called an intercalated year. This is most typically taken as a work placement, so if someone wants to go away for a year and work in industry. But it's also possible to do the intercalated year as a study year abroad or as a year in research. So you can work with a research group within Warwick or also elsewhere. Another degree that we partner on within our department, but is not directly hosted within our school, is the Computer Systems Engineering degree. This one is also available as a BEng or MEng. And it's our flagship degree with the Warwick Computer Science Department, which is another great, excellent department, very highly ranked within the UK. So they combine computer science with some specialized engineering content on the design of electronic systems. The way that this degree is structured, it has less flexibility. So if you take this degree, you have to start from year 1. All the other courses have a joint first year, but the computer systems engineering first year is different. Some of the benefits of this degree include full access to both the facilities and staff in both of the departments. So this includes having a personal tutor. You'll have a personal tutor in computer science as well as a personal tutor in the School of Engineering. This course might be particularly of interest for anyone who's interested in software and hardware and how they work together. Although my completely unbiased systems engineering background or involvement in the department, I would also say that you get a lot of that in the systems degree as well. But in any case, if you are interested in this particular program, you can get that from the computer science department because they handle admissions. It's direct entry through their school and not ours. We also offer apprenticeship degrees. So these are heavily integrated with industry. They offer a lot of hands-on industry experience. These usually take about 5 years, and you actually apply through the company that is offering the apprenticeship. And then it includes frequent periods throughout the year where your cohort of students, you will all come to the university for a short period of time, say a week or two, to take part in lectures and labs, and you'll go back to working with the company. So right now we offer 2 different courses on this apprenticeship degree program. So we have a BEng in Civil and Infrastructure Engineering. This one we started about 6 years ago. And more recently, we've started also a BEng in Electromechanical Engineering. And the logos here show some of the companies that are involved in supervising the apprenticeships through the apprenticeship degrees. So the course structure for all the traditional degrees, so not the apprenticeship ones, as I mentioned, there's a first year is common, and this is for all courses except the Computer Systems Engineering program. And this common core first year covers a lot of engineering fundamentals. Many of the modules that you take will kind of sample across the different streams. And I'll go over the list of modules a bit later so you can see how that lines up. But we let the students specialize at the end of their first year. So from second year onward, you'll be taking modules that are more specific to your chosen discipline. So you'll be getting more of the specialist knowledge. In terms of BEng, MEng, we offered a fair bit of flexibility kind of in being able to switch between them. So if you're a student that's on a BEng track, if your performance is at a level of 2-1 or above, you can choose to upgrade to MEng at the end of your second year. It's also a possibility, although it's less formally structured in this way, that you could also upgrade at the end of your third year. So you can literally be about to be handed your degree, not literally, but you can be very close to getting your degree and then decide, oh wait, I'll stay for that extra that fourth year to do the MEng course. And there are some people that do that. For the intercalated year, I would say the main constraint is that you need to have a year to come back to. So if you're on a BEng stream, you would normally take the intercalated year between years 2 and 3. And then if you're on the MEng, you could also instead take your intercalated year between years 3 and 4. But you can't go on an intercalated year, say after year 3, and then decide to graduate. You have to be able to come back and still do an additional year if you're on the MEng group. And just to iterate the point that the engineering business management degree does not have the MEng option. So if you're in the EBM course, you're kind of locked in there for doing the BEng. For entry requirements for MEng, we require at A levels a score of A star AA in 3 subjects. We do, however, make dual offers. So anyone who applies as an MEng and is successful, they will have both an MEng offer and a BEng offer. So they could accept either one. Though, as I was sort of going over in the previous slide, we kind of let people shift between the two if their performance enables that. So that's not a big difference. However, for the BEng, we do have a lower entry requirements, and that's just 3 A's in 3 subjects from the A levels. Whether you're going BEng or MEng, it's required that 2 of your 3 are math and physics. It is possible and that you still could be considered for entry if you have a strong profile, but you're missing either the math or the physics. But it's certainly the case that you definitely need at least one of them, and certain your personal profile might be considered if you don't have both of them. But it is still possible to be considered for entry. Anyways, the default is having math and physics. That's the cleanest entry into the school, is having 2 of those among your top 3 A levels. For accreditation, all of our school zone degrees are accredited. So if you do an MEng, this is probably the biggest difference between MEng and BEng from a long-term career perspective. If you're interested in becoming a chartered engineer, there's an educational base is one of the requirements. So this is basically a box you need to tick. And if you have an MEng degree from one of our school's degrees, that fully ticks that box. So the MEng degrees are accredited as fully satisfying the educational base. If you do a BEng degree, it will only partially tick the box. So you would, if you finish with a BEng and you're interested in becoming a chartered engineer, you would have to do some additional courses and learning in order to be able to fully satisfy the educational base for being chartered. In terms of the degrees that are outside of School of Engineering, the Computer Systems Engineering degree, that one is accredited separately, so you'd have to refer to that department for the latest on their accreditation. Furthermore, if you do the Engineering Business Management degree, because that one has a greater breadth that includes a lot of project management and financial elements, that one's not designed to lead to chartered status. So if you do that degree, you would not be satisfying the educational base for becoming a chartered engineer. Mind you, those graduates still do very well. They just end up more in, let's say, project management, administrative type roles, as opposed to technical ones. And becoming a chartered engineer is really a technical qualification. We show here some of the logos of the different bodies that are involved in accrediting the different degrees. Basically, these are split up into different industries, and there's a bit of a cross section. So a number of our degrees are accredited by more than one of these different institutes. So you'd have to check our website for kind of the latest details on who accredits what. But we do all have all that information available. So that was a bit of a general overview of the different degrees. Now I want to elaborate a bit more on how teaching and learning looks like in our school. Our academic year is divided over into 3 terms. We have an autumn term, October to December, a spring term from January to March, and then a summer term from April to June. Students normally complete 120 credits per year. So if you do some math, you can work out that the 4-year MEng would be 480 credits and the 3-year BEng would be 360 credits. A typical module is 15 credits, and we estimate effort or a time commitment to be about 10 hours per credit. So that would be a typical module then would be about 150 hours of work. 30 hours of that would be contact time. Contact time would include lectures, time in the labs, any kind of session that involves the module instructor. And then the remaining 120 hours would be guided independent learning. So this could be working on assignments. This could be studying for the exams, reviewing module material, and so on. The main exceptions to this typical structure are the large projects that are done in year 3 and year 4. So these are double weighted. These projects are worth 30 credits or 300 hours roughly of effort. And so they're structured a bit differently, and obviously they make up a big part of the program because each one is 1/4 of the credits you would earn in the given year. For class sizes, we have quite a range. Even in the first year, your tutorials for math are very small. So I mentioned before that your personal tutor is the person you would be doing your math tutorials with. So usually a tutor has about 6 tutees assigned in a given year. So when you do your weekly math tutorials, you'll just be in a group of up to 6 people. Up to larger lectures, you can have up to about 350. That's about the intake that we get on a year-to-year basis. And that's the first year intake, doing all the common modules. So as people select their disciplines and then they kind of merge off or branch off into the different degrees, the classes tend to get smaller and smaller. So you get to a point where in more specialist or optional 3rd year and 4th year modules, you might only have 20 or 30 students in an individual module. The assessment is really a mix of coursework, exams, and project work. We do have both individual and group projects, and I'll have examples to give some representative information for all this in the following slides. So our overall teaching and learning strategy really uses diverse approaches for learning. Our overall model kind of has 4 main types of teaching and learning activities. And I'll go over examples of all these on another slide, but we kind of group these under face-to-face lectures. That's kind of obvious. Directed asynchronous learning. This could include pre-recorded videos that are covering lecture material. And obviously that was a much bigger thing in the pandemic years, but we found we have a really, really good pool of resources that we are able to keep using where we can for supporting the more conventional lecture structure. We also have learning by interacting sessions. So this can include kind of like seminars, discussion groups, example and tutorial sessions working with the instructor as different ways of supporting the asynchronous learning. And then we also have learning by doing. So this would be labs, project work, and so on. Our delivery of technical content for most modules is structured around what we call the learn, apply, and reflect model. So this would mean that we have content that you learn, so a concept that you'll learn. You'll be given opportunities to apply that learning, and then you'll have opportunities for reflecting on what you've learned. And we'll see some examples of this when I go through how we've structured some of our online content. But this really is a general approach that most of our modules currently follow. In terms of the diversity of teaching and learning activities, these activities could include lectures, example classes, labs. So a lot of modules, especially in the early years, they'll have quite regular lab sessions for enforcing the material that you're covering in lectures. We have computer-based classes, so these include programming, analysis, CAD software that you'll get to practice with, so CAD being computer-aided design. We have our tutorials, so these would be generally smaller group teaching with an instructor or some other facilitator. We have design and build activities, so really kind of building upon what you learn in the more fundamental lab sessions. And we also have projects, and the projects are generally tackling real-life problems and are really the highlight of the courses that we offer. So some of the types of projects can include design and makes. This would be making some kind of prototype of a product. We have restoration or recommissioning projects. So these would be a project where there's some previously existing product and we're trying to, let's say, upgrade it maybe to meet current requirements or criteria. We're finding some way to recommission a product that's able to perform some new purpose. A number of our projects are kind of design evolutions of high technology or high complexity systems. So there's lots of good examples for this, particularly in our fourth year projects. So these are group projects that have fairly large groups, let's say 6 to 8 students, usually coming from different disciplines. I've been running a project on autonomous drone flying. So I've had a group that's been building a drone every year for the last 6 years. And from year to year, the applications vary, the focus of the technologies vary, the features vary. So even though there's, let's say, a drone, it kind of gets rebuilt every year. And there's quite a few projects that follow a similar approach with cars and submarines and so on. It's also possible, especially for the third year individual projects, to get more purely theoretical or computational modeling in the projects. So those follow more, say, computer-based and theory developed. So working on, for example, some entirely new idea that hasn't really been developed yet into a technology. We do have work involved kind of in that high level, early level sort of research. And of course, a lot of these projects, you have direct supervision and support from academic staff. So as a assistant professor, associate professor, full professor who's working with you or your group on making sure the project progresses smoothly. In terms of our hardware facilities, the highlight is our engineering build space. So this is our flagship design teaching facility. This is a large lab we have on the first floor of the engineering building. It supports, of course, the teaching of our design modules, but we really do use it for a broad range of activities. These can include modules that are less design focused. Many students use it for individual group projects. Of course, we have 3D printers and lots of other equipment for cutting, soldering, and so on. We run open days there as well. So if you come to Warwick for an open day, we do run tours through the facility, so you can check it out then. We do run design jams during the academic year. So the big occasional weeknights when the space will be opened up, and then anyone can come in and use the facilities there, whether a student or staff, and they can work on whatever they want. It can be a personal project, it can be something they're an idea they're just trying out. It doesn't have to be related to any specific academic activity. We just make the facilities available for students. And of course, we also use the facilities for direct research, either by our postgraduate staff or our academics make use of it as well. A bit about the numbers and the breakdown. So I talked before about having kind of time that you spend in the class and time you spend on other things. This is a table giving a rough idea. These numbers aren't set in stone, as they can vary a bit from year to year, but they give you a rough idea of how the time gets used up. So I already mentioned 120 credits per year, so that would work out to about 120 hours of study time. And the main trend I want to point out here is that in the early years, you spend relatively more time in lectures and seminars than what you do in the later years. So there's a trend where the lectures go down as you progress, and the time spent on projects goes up. Particularly the big third year and fourth year projects, which I mentioned were 30 credits each or 300 hours. And independent study stays more stable year to year. But this gives you a rough idea of how the program evolves as you progress, and then you spend more time on projects. For assessments, similarly, you'll find that the assessments are weighted more towards exams in the first year or two. And again, as you progress, there's less of a focus on exams. That tends to go down, and the weighting towards projects tends to go up. Coursework stays a bit more steady from year to year. But overall, you do experience a variety of assessment methods. The exams that we give, we still do some, though perhaps going forward, not too many online remote exams. But But what's more common now is we run our online exams in person. So this gives students, we'll have run an exam in a computer lab where the students will work through the questions, but it'll still be invigilated. So there'll be academics and other support people in the room to make sure that we are able to maintain the academic integrity. And we also have written in-person exams. So these are more traditional. You have an exam book and an exam paper, and you fill out the exam booklet with your answers. The virtual learning environment. So we do have a website, an internal website called Moodle, where we have much of our lecture content and course content. This includes lecture slides, lecture captures. So we have videos get recorded for many of our lectures. In addition to the live recordings, we can also have pre-recorded videos available there. We have quizzes, we have like lab assignment briefings, and so on. This is just an example layout for one of our first year modules. This is one on system modeling, simulation, and computation. And the platform is kind of organized by week. So as you progress through the semester, through the term, you can access the different content that's available. And just to show you kind of a bit more detail for this systems modeling module, this is some of the content for week 3. And just to show that we do follow the learn, apply, reflect model. So we have the learn component is having lecture content, slides, and related readings that are provided. There's even a time estimate here for how long it should take to go through the lectures. For application, we have online labs, we have practice quizzes, worksheets, other links that help support those activities. And finally, under reflect, we have support and feedback opportunities. This can include accessing the support and feedback hours of the instructor to go and ask questions, or to access, for example, forum pages or FAQs that are specific to that module and the students that are enrolled in it. So this general approach, you won't find this exact layout for every module, but this gives it's a great example of how we structure much of our academic content on our degrees. So the first year modules I mentioned before, that it's a core first year. Students take 8 modules. I won't go over all the details of all of them, but just to kind of skim through the titles so you get a sense of the flavor of what all the students will cover in their first year. This includes dynamics and thermodynamics, electrical and electronic circuits, engineering design, engineering mathematics, engineering business management, professional skills, engineering structures, materials for engineering, and then finally systems modeling, simulation, and computation. So you can see, I think quite readily, how most of our courses align quite well with these individual modules. And so the core first year really helps give you a sense of the flavor of how the different courses are designed. We also run information sessions during the first year from the different directors of study of the different degree programs. And that's to give opportunity for them to come in and really actually talk more specifically about the individual degrees and the content and the modules that the students complete as part of those courses. We do also have a number of projects that are run, particularly in the engineering design module and the systems modeling module. We have a number of group projects, even in the first year. And they're great also for introducing you to some of the software that we use, particularly MATLAB and the CAD softwares like SolidWorks and Fusion 360. And they cover quite a variety of topics, kind of reflective of the different disciplines that we have in our school. So as I already mentioned, beyond first year, students pick their different courses, and so then they have the corresponding modules. I won't go through all the details. There's a QR code here for our engineering brochure, which actually gives the list for 2025 entry of all of the core and optional modules on all of our degrees. Just to summarize them a bit, I just want to point out that most disciplines do have a project module in the second year. In the third year, the big project that students do is an individual project. That one's worth 30 credits. And so that one is you're working directly with an academic, you're usually meeting with them on a weekly basis to do a sometimes quite research-focused project, or you could be building something of interest. And these are individually selected. And then for those doing the MEng, so in the fourth year, there's a large group project. So like as I mentioned earlier, with project working on building drones. There's lots of other group projects working on race cars, submarines, biomechanical test beds, and so on. And they all involve students from different programs. So, for example, on my drone project, I have electrical, electronic, mechanical, manufacturing, systems, computer systems engineering. I get students from all across the different courses selecting that project and being assigned to it. So you really do get a great diverse group of students with different skill sets that can really integrate together for these big group projects. Just as an example of one of the more, let's say, high-profile projects, we do have a satellite project that's been run for the last 18 years or so now by an academic, Bill Croft, who's been very active, and he's gotten the support of both the European Space Agency as well as many industry partners, and they've run many successful iterations. The applications change every couple of years as the project kind of refreshes, and they've been involved in a number of launches and being able to have their results kind of shot off into space, kind of in low orbit, and they've been able to have platforms where they're communicating with the satellites to collect data and help perform some research and gather measurements of interest to the European Space Agency and others in the aeronautical industry. Some other more engineering projects, I won't go into too many details, but we have lots of robotics. I mentioned submarines, biomechanical modeling. So we have a gate lab where people can get covered in these dots, and then we have cameras that track where the dots go. This is great for biomechanical modeling and being used to come up with health technology supporting devices and so on. And then we get more civil-based projects like building design, other kinds of robotics and racing and so on. So quite a good diversity of projects available. So the next few sections will be a bit faster as I go through certain elements of kind of student life and life of the university and support that we provide. So starting with the student experience, we do run a lot of activities in a given academic year. This includes a welcome week, especially for first years. We have it's a week full of kind of icebreaker and welcoming activities. Students meet their personal tutors and so on. We have reorientation days. So every semester, the students from different courses will get together with their director of study, and they will go over kind of updating on important details and logistics for the given semester. We run Getting Connected events for students and staff to interact. I already referred to the design jams and the build space. We run New Year parties every January for students. We run all kinds of workshops, and we obviously we have receptions at our graduations. We have graduations in January and July, and those are always big celebrations. And some of the pictures here reflect those. More broadly across the university, there's lots of student clubs and societies. The university has over 300 student-run clubs. We're quite a diverse campus. We have over 150 nationalities represented. It is a campus university, so we're just on the outskirts of Coventry. And so we do have quite a lot of space available, and this includes about 60 acres of outdoor playing fields for football, rugby, and so on. In addition to the university-wide clubs, there are a lot of clubs that are specific to engineering. This includes Engineers Without Borders, Warwick Racing, Warwick Women in Science Engineering, and lots more. I want to draw particular attention to the Warwick Engineering Society. So this is kind of the main student society for our department. They run some annual conferences, industry site visits. They do a lot of career events, social activities, academic sessions, and workshops. They really have quite a busy calendar. The pictures that I grabbed here were from just a few of their ads on Instagram from some of their activities from the current academic year, and they're quite active. And so it's a great support for students when there's a really active student society available within the school. A bit now on placements and career pathways. So we do provide a lot of different support. Obviously, if you're on a degree apprenticeship, you're already in a company throughout your whole degree. But even if you're not, we try to provide a lot of resources and information and support mechanism for students. This includes having a careers office where they can give a lot of one-on-one support. This can include support for job interviews, help with working on your resume, and so on. We have career fairs where we have companies come in. We run employer talks, particularly within the department, where industry representatives come and talk about some of the recent projects that they're working on, and so on. We do have quite a lot of resources available. This includes trying to provide tools for success for students to have after they graduate. This can include help with finding placements over the summer or on year-long placements if they're doing an intercalated year. And we have a specific individual. Our department has a student engagement officer who's quite involved with making sure students are aware of these resources. And at the university level, we also have a careers and skills service. So they can do a lot of one-on-one support sessions. And they run a lot of activities as well. There's a careers portal where people can look up, for example, job vacancies. I grabbed this screenshot earlier this year, and at that time there were 217 graduate employment vacancies available. So these are all looking for people that are just finishing their degrees and looking for work. So even within our own database, we have quite a lot of opportunities that do get shared with students. On the financial side, I just want to briefly say we have a number of funding programs for incoming students, particularly the ones I draw attention to here are Global Excellence Scholarships for international students. We offered a Warwick bursary for students coming from households with limited income. We have a competitive Women in Engineering Scholars program that has applications that open up in the autumn of every year. And also for asylum seekers, we do offer full tuition support and maintenance through our sanctuary scholarships. There's other work you can do while you're a student. This includes our ways of getting money by working within the department. This includes the undergraduate research support scheme. This is run across the university. We also have a department-specific one, our School of Engineering summer research internships. Both of these programs run during the summer. You do a research-based project, either in our department or in some other department, and you can get some money towards living expenses. Furthermore, we also have an ambassador scheme. So you'll find that all of our recruitment events, we do outreach and public engagement. We do hire a cohort of students to help support those. So that's an opportunity that's available for students to help become ambassadors for the department across many of our recruitment and outreach activities. Finally, I'll talk briefly about some of the support we give for students who come to our school. We do run a website, a web page that has a lot of information and practice sessions. This includes introductions to individual tutors and people who are directors of study on the different courses. We have a number of research-based talks available. We have a version of this slideshow I'm giving here without the research part, but I myself or someone else, if we update the video, we do provide a presentation about our degree. We also give resources for information about the different courses, the student societies, our facilities, and so on. We also run regular live chats, so people who are interested in applying can check out one of the live chats to chat with current staff and students to learn more about the department, particularly if they have any questions. This is quite a useful web page for those who do come to Warwick. Just to show some screenshots from some of the virtual taster sessions. These are just taken directly from some of the recorded videos from the different modules, particularly from the first year. So we just give a sample of this is what it's like to learn from the different degrees that we offer. And we also provide access to a platform that is specific for brushing up on your math skills. So making sure that your A-level mathematics is if you hadn't covered everything or if you have any gaps in your knowledge, we have a particular platform to help catch up on this on your own pace before you start on one of our degrees. So that's about it. I do welcome if you're interested more in our programs, check out our website. There's a QR code there that will take you to our undergraduate web pages where you can see a lot more about our individual degrees. And you're also welcome to follow any of our social media channels on Twitter/X, Facebook, or Instagram, where we do regular posting of the successes in our degree, and you can learn more there. So thank you very much for your time. I pleased to go back to the conversational mode, if you will. Yeah, there we go. Hi.
Great. Hi. Thank you, Adam. That was great. Oh, there's a lot to go through.
It's a
Um,
bit of a whirlwind,
yeah,
I'm afraid.
it's such an exciting area. And there's so much to cover. And so thank you for doing it in such an engaging way. I know it's quite difficult over the internet
Sure.
without
Yeah, yeah.
group interaction. Have you got any specific questions about research, or is it generic questions about engineering, or
Got a generic question about the university.
far away?
Yeah.
Hi.
What do you think makes Warwick a better university than others for engineering?
Well, I think being a general school really contributes to how it is able to give an integrated degree. That level of diversity, having a common first year. Okay, yes, there are trade-offs. I think a lot of students, when they're coming out of secondary school, even if they're interested in engineering, they're often not sure exactly what type of engineering they want to do. And it might not be that they're indecisive, it might just be they're not aware of what's available. So we do find a very large number of students. We do tend to see, like, many students that come into our school are either coming in under mechanical or general. So either they think they know what engineering is, they associate mechanical as being the default one, so we get a lot of students on the mechanical stream, or they recognize they don't really know what they want to commit to, so they go on the general stream. And many people then will switch out of those as they progress. Not to say that the general or mechanical programs are poor, but just the once they have more knowledge and they're armed with having a general studies year and really getting a sampling of the different types of engineering, they're able to make a more informed decision, which can really be quite helpful. Um, I think also with Warwick, there are strengths with being a campus school. It contributes to being kind of a close-knit community and a close-knit department, um, in a location that's quite suited for that. So that's really quite helpful as well. Yeah, those are probably the biggest elements I would go through. I mean, I could go on again, but I think I would be repeating a lot of stuff that I just went over in my presentation. But I hope that was helpful to answer the question.
Excellent. So that first year seems like settling in and actually learning new things, which is very important.
Yeah,
There'll be loads of things that you just don't understand about engineering until you experience them. So it's quite refreshing, really, that you could swap onto a different discipline. I've got a specific question, if I may. So
sure.
you were describing your research, and I was just thinking about all the technology that goes into that and how that might impact on the lead time to market of new drugs. And
Sure.
my second question is really, how is using that technology in pharmaceuticals um, accepted across international borders with different laws?
Sure. Was that one question? I heard that was one question. Was
That was definitely There was
the
sort of
question
two
the
questions. It
lead
was,
the lead time bit? Okay, sure,
yeah,
sure,
the
sure.
lead time and also the different legislation.
Right. Yeah. I mean, I would say that the research that I do is at a technological readiness level that the, let's say, current landscape of drug regulations doesn't is not quite ready for this kind of stuff yet, let's say. But I know with the project, so currently what we're doing with AstraZeneca, with these organ chip platforms, what they're really interested in is replacing animal models. So they want to at least decrease, if not eliminate, the reliance on needing animals to do testing. Um, and the idea of having these organ on chips designed in a way to try to mimic human physiology, not saying that that's an easy thing to do, it's a very challenging problem. But the goal is to try to design the system in a way that you can more readily scale results. Because when you go to, let's say, full clinical trials, um, a problem with relying on animal models is that when you go to human trials, you'll end up with drugs not working the same way as what they worked on animals to begin with. Besides, so you could have efficacy issues, and then you also could have toxicity issues that weren't identified previously. Um, and those are both things that having an organ on chip platform is trying to address. Um, at the very least, what it would accelerate is the ability to test a larger number of drugs much more quickly, because you can have this experimental platform. It really lowers the cost, or at least it lowers the developmental curve in being able to do drug testing. So it's overall it's envisioned to be able to cut down developmental times. It's such that you can identify drugs for human trials more quickly. You still have to go through the human trial process, um, but the idea is to have to make more informed decisions if we can before hitting that stage.
Okay, thank you.